Oh, yeah, this is a really good book. It's so old, though. Uh, oh, okay. So I want to show you an interesting scenario that often occurs in the lab when we're studying gases from chemical reactions. And this is a scenario that would be quite similar to your next lab experiment next week. So here, it's funny, we have like some kind of tubing here, and the idea is there's like an apparatus over here that a chemical reaction is taking place that's bubbling and producing a gas, and the gas fills that tubing and comes down here, and we have an inverted glass container where the gas bubbles through and starts to fill up here. And there's water in there too, so there's like some water vapor that also fills up this closed container. We know about the vapor pressure of water. And so much gas is being produced that in this picture, it's saying, oh, you've put enough gas in, so it's pushed down this water level all the way down so that it's level with outside. And that's an interesting scenario because if you have it exactly level, then you know what the pressure inside is. It's the same as the pressure outside. That's barometric. You could use a barometer to measure the external pressure acting on the water surface. And because these levels are the same, you know that's the same pressure as what is this gas. So in your experiment, the type of gas you're going to be producing from a reaction is nitrogen. So what happens is in here, this pink, it's not pure nitrogen, it's nitrogen mixed with some water vapor. So there's a mixture of gases in there. You can't help but water just sort of detaching from the surface and producing a little vapor pressure. So this is pretty common. It's hard to find a pure gas. Most of the time we're dealing with mixtures of gases. So in that case, we'd like to apply what's called Dalton's law. That's not a big deal. I mean, PV equals nRT is still good, but it's the pressure part of PV equals nRT that we want to dissect into a couple of components. In this situation, it would be like the pressure exerted by the nitrogen plus the pressure exerted by the water. That total is equal to this external pressure. And if you're not dealing with nitrogen and water and you deal with all sorts of other gases, you could more generally write Dalton's law as like PA plus PP, is total, where A, B, and C are the identities of different gases. So the total pressure of a gas mixture is equal to the partial pressures, instead of total, partial pressures of each gas in the mixture. Just sum them up. That is Dalton's law. So what can we do with that? Well, one thing we could do is start to realize that if you have a lot of nitrogen being produced in a reaction, that's certainly going to be proportional to the total. More nitrogen will give you more total pressure. And from PV equals nRT, any pressure is expressed as nRT over V, PV equals nRT, and the N here is the number of moles of nitrogen. And so if we want to say the total pressure, that's going to be number of moles of total pressure times RT over V. Now, they're not equal. They're proportional, but not equal. To make them equal, we need some sort of proportionality constant. So I wonder what that could be. Wonder what that proportionality, how can we make the left side of this equation and the right side of this equation be the same? I got to change the right side of the equation so it becomes that. I mean, the RT and V are fine. It's the N mole. Like, what if I put N of nitrogen here, and then I have N total there? Oh my gosh, both sides of the equation are equal now. That's pretty cool. But this, maybe you recognize. This is something special. This is something we encountered last semester. This is mole fraction. That's a mole fraction with respect to nitrogen. Number of moles of nitrogen over total, a fraction, just in terms of moles. So now we can say, hey, the pressure due to nitrogen in a gas mixture is equal to the mole fraction due to nitrogen times the total pressure. The pressure of one gas in a mixture is equal to a fraction of the total. Yeah, it's a contributor. But this is kind of a handy formulation of Dalton's law because we can do things like this example. So We're at example 4. Example 4. We got a mixture of nitrogen and water, and somebody's counted the moles of each. And then the only measurement here is the total pressure. What's the partial pressure of each gas? So we don't know like volume or temperature. We don't know those other, so we can't use P equals nRT, but we derive from P equals nRT this nice relationship. So we can get the pressure due to nitrogen first. It wants each gas, so the pressure due to nitrogen first is equal to the mole fraction with respect to nitrogen. We got 0.100 mole of nitrogen over the total moles, 0.8 and 0.1, that's 0.9, times the total pressure of 842 millimeters of mercury. It's okay to keep it in those pressure units. As long as we're consistent, it's fine. It's only the temperature you always have to change to Kelvin. All right. So, so the partial pressure due to nitrogen is 93.6 millimeters of mercury. Yeah, let's think about that. There's only 0.1 moles of nitrogen out of 0.9. So yeah, out of 842, yeah, it's that small fraction, just 93.6 millimeters of mercury. So how do we get the partial pressure of the water? Well, we know the mole fraction of nitrogen plus mole fraction of water adds up to 1. But then we also know the partial pressure of nitrogen plus the partial pressure of water adds up to the total. So might as well take our 842 minus 93, and then we get our pressure due to water. That would be the vapor pressure of water. And that's known in databases according to temperature. So you could probably look that up. That's what you'll need to do in your lab exercises. Look up the vapor pressure of water at the temperature of your experiment. Isn't that great? All right, so just a reminder, no classes on Monday in honor of Dr. King. I just wanted to share this little quote from him. He wrote a lot about faith and science. Dr. Martin Luther King Jr., he said, "Science investigates, religion interprets. Science gives man knowledge, which is power. Religion gives man wisdom, which is control. The two are not rivals, they're complementary." Yeah, that's how Dr. King felt about science and religion, particularly Christianity. So, reminders, prepare for your experiment well on Tuesday and Wednesday by reading through the introduction and procedure, and make sure you complete your experiment number 1 report on time. And that is it. Thank you. Thanks for your prayers.